So I would like to begin by acknowledging that my work is part of a large collaboration between the Deep Prints group at FSU and other research groups from the University of Washington, Virginia Tech, and Lawrence Berkeley National Lab. So one of the goals of our project is to help design materials for quantum computer. So imagine that you can store information in molecules and which act like magnets that we have learned before, and they can have up direction or down direction, which you can think of like the ones and zeros in your computers. Now, experimentally, we want to be able to measure the energy spacing between the up and the down states, but this can be very difficult to measure experimentally. So, as a computational chemist, what I do instead is take this molecule and then I design models based on math and physics, derive equations, and write a computer code that can give me the data that I want. So, ideally, these models should be fast, they should be systematic and accurate as well. So let me give you an illustration of one such model that I actually use in my day-to-day research. So we know that molecules consist of atoms, and in each atom, you have the nucleus consisting of protons and neutrons, and you have electrons that go around the nucleus in a region of space we call orbitals. And these orbitals can be filled or they can be empty. Okay, so with our models, we describe how these electrons move around the nucleus, and we can make the model more accurate by moving the electrons one at a time or two at a time, and by moving more and more electrons at the same time, we make the model more accurate. But this is not enough. We also need to increase systematically the number of orbitals that we use to describe the molecule. So in doing so, we increase the complexity of our model as well. So this is an example of a work that I did during my PhD, where we look at light coming out of two magnesium atoms vibrating when in experiments you shoot light at it. So here you can see our simulated data in red, which matches exactly the experimental data in black. And if you zoom in at this region, you see that our simulation can predict things that are buried in the noise in the experimental data. So in order to do this, we have to move a lot of electrons at the same time, and we also have to use many number of basis sets. So if this can give us very accurate result, so what's left? So I can tell you what's left. It's relativity, which happens when we go down the periodic table and the atoms become heavier and heavier, and the electrons start moving faster and faster. So as the electron travels faster and approaches the speed of light, then weird things start to happen. For example, with relativity, gold becomes yellow instead of the usual silvery metal color. Relativity can also split your energy levels that I mentioned, so now you can observe more things in your experiment than expected. And actually, because of relativity, your car can start, because now the car battery have enough voltage to crank the engine of your cars. So how does relativity change my model? Well, I have to design orbitals that can accommodate the faster moving electrons and also account for the splitting in the energy levels. And because of that, now I have to account for another axis in this accuracy graph, which is how accurate I describe these relativistic effects. Right? So the bottom line of my research is balancing the cost or complexity of these models with their accuracy. So we got to start small. So this is an actual work that we did where we look at two copper, silver, and gold type atoms that we stretch, and we just look at the energy, and we check all the boxes in the accuracy graph. And you can see that if you use good relativistic orbitals, you can pretty much match experimental data. But this is still far from the molecule that we want to target. So how about I offer you two more atoms? With 4 atoms, now what we did here is we kick one electron out, and you got to be careful, because if you do it carelessly, your orbitals can become wonky and your energies become weird. We use theory that avoid that, and you can see here that, again, we can reproduce experimental data nicely. So all of these are basically just baby steps as we work toward better and more cost-efficient models, so that one day we can simulate this single molecule qubits that we want to target. So Thank you for your attention.